Salutations, Internet. Good time zone. All right. Well, I hope you enjoyed your week. We're going to start out by doing some housekeeping and acknowledgement of equations. So I have the two equations that we looked at in the previous example officially. And then I have this extra one here, which is not on my equation sheet, but since it came in handy during the previous episode, I decided to go ahead and include that. We'll be coming back to this one later. The other housekeeping point is that towards the end of the previous episode, I talked about uh, how you can use numerical methods or graphical methods when algebra fails you. I think I will do a video on tentatively. I might do a video on that, like after I finish filling out this section. But I'm not entirely sold on it. Like I said, it's kind of a pain in the neck to do. But depending on how crazy that gets, I might do that. So keep an eye out for that. But right now, we're going to go ahead and get started with the episode. And like I said, we are going to be looking at this equation right here, this one that helped us out in the previous video. So let me go ahead and copy that over to here, our blank workspace. Cosine of the eccentric anomaly angle is equal to, and I'm going to write it like this, AE plus R cosine of theta all over A. And as I've pointed out that I like doing before, many times by now, we have an equation here that's filled with A's and E's, and we have this one R here that we know can be expressed in terms of A's and E's. So let's do that. We have a couple of options to choose from now, actually. We have our new equation and where's the other one? There it is. And our previously defined orbit equation. I'm gonna say let's look at this one, since we're already trying to do a conversion between theta and E. So let me write that in here. A 1 minus E cosine of the eccentric anomaly angle. Then we'll plug it in. Try to make my handwriting look a little bit neater. Some days you just have nice handwriting and some days you don't. You know? A times E plus A 1 minus E cosine of E times the cosine of theta all over A. And I'm gonna mark these out in red. We don't need these semi-major axes anymore because they will cancel out with each other. So when we rewrite it, we can fit it all on one line now. We have that equal to eccentricity. I'll go ahead and I'll distribute plus the cosine of theta minus E times the cosine of E times the cosine of theta. Well, we have an eccentric anomaly angle here. We can move it over to this side. I'm going to go ahead and take out the cosine of E. I almost said undistribute. That's probably wrong. So we have cosine of E times, I'm going to use brackets for this. We have 1 from this guy, and we're going to get plus e cosine theta from that guy, plus e cosine of theta. That's equal to the parts we left behind, eccentricity plus the cosine of theta. Solve exclusively for e, at least the cosine of e. I'll probably stop there. Equals e plus cosine of theta over 1 plus e cosine of theta. And that is a good equation to have for converting between from theta to eccentric anomaly angle. You can use this. There is nothing wrong with using it. We used it in the last video. It works. It does what it's supposed to do. But if you're not given the size of your orbit, you may want to give this one a try. It's just a little bit neater. The only thing you need is what shape your orbit is, so eccentricity, and where you are within it, your theta. This, however nice this equation is, does present us with a bit of a problem, because when you take an arc cosine and you're trying to find an angle, you will get a value somewhere in quadrants 1 to 2. So if we have our quadrants here, we have quadrant 1, 2, quadrant 2, quadrant 3, quadrant 4. Arc cosine is only ever going to give you something in this region, which is how do I want to describe this? It's not awful, but it's not the best either. So one equation to rule them all is apparently not the way to go. It's not always. We'll touch on that here in a little bit. So this is a good equation for determining if you are in the left half or right half plane of your origin. If you want to narrow that in, you're going to need to use another function. You're going to need another equation. And fortunately, we touched on one. We touched on that topic a little bit in 2 videos ago, where we have this guy right here. So we're going to use this sine equation here, not star, times. We are going to use this equation to supplement our cosine equation so that we can hopefully narrow in on a more accurate angle. So let me copy this over. That is, give myself some more space. A times the sine of the eccentric anomaly angle is equal to A over B times R times the sine of theta. And let's make it messier to make it easier to work with, right? So let's look at A over B. That, as I touched on, I think in that same episode, can be broken down to become 1 over the square root of 1 minus the eccentricity squared. And this is the circle to ellipse ratio. The other thing that would be useful here would be to look at radius. And for this one, I think we're going to have an easier time if we look at our orbit equation. But I don't want h squared and mu. I don't feel as though I need that. So instead, we're Where'd it go? There it is. H squared by mu, I'm going to replace that with a times 1 minus e squared. Because in this equation, once again, we have a's and we have e's. So a times 1 minus e squared over 1 plus e cosine of theta. Theta, not g. So let's go ahead and plug all that back in. We have a times sine of the eccentric anomaly angle. That is going to be equal to a over b becomes 1 over the square root of 1 minus e squared. Very nice. R becomes a 1 minus e squared over 1 plus e cosine of theta. Very, very nice. Times the sine of theta. All right. So our a's will cancel out. And then because of the way that exponents work, our 1 minus e squared in the numerator goes from a power of 1 to a power of 1/2. So we'll square root it. And I will scoot down here to give me some more space. That is going to become sine of the eccentric anomaly angle is equal to the square root of 1 minus e squared times sine of theta over 1 plus e cosine theta. And yes, that is the final equation for sine. And this has much the same issue as cosine did, in that it will only give us a number between minus 180 degrees and positive 180 degrees. So again, if we look back to our grid here, where we had 1, 2, 3, and 4, this is only going to give us values in this side. Said another way, the upper half plane and the lower half plane, and the two of them combined will get you a value that is very specifically in one plane, or one quarter plane, one quadrant, that this is where your orbiting body is. And just to really hammer that point home, we'll do an example. This is going to be a quick setup. We will need an eccentricity, and we will need a theta. And here's where I pull the rug out from under you guys. We're going to be looking at a different eccentricity. And a different true anomaly angle. This is a completely different orbit. Doesn't matter how big the orbit is, as we've seen from the other equations that we've derived today. So let's go ahead and get started. And I will start with the cosine. So I'm going to use that equation. Here's the arc cosine of yeah, and I'll go ahead and I'll plug in the numbers now. 0.65 plus the cosine 225.76 degrees over 1 plus 0.65 times the cosine of 225 degrees. And plugging that in, that's going to give you a number of effectively 95 degrees, 95.00 and change. All right. So we're happy with this, right? We have ourselves an eccentric anomaly angle. Except this doesn't quite sit well because our true anomaly angle, let's go over here. Let's go over here because I already have it drawn up. Our true anomaly angle, what did I say? 225 degrees, puts it past this line all the way down here somewhere. So if I were to, tell you what, so if we were to do this, which is close enough, then we have our host, the Earth, at one focal point, and we have our origin here. Our eccentric anomaly angle is saying that we should be pretty close to 95 degrees, or to straight up. Except we are looking at something that is down over here somewhere. So clearly something's not right. So it's a good thing that we have that second equation, that sine equation. And in fact, let's go ahead and solve using that equation now. We have the square root of 1 minus 0.65 squared times the sine of 225.76 degrees all over 1 plus 0.65 times the cosine of 225.76 degrees. That's going to give us a number that is remarkably close to minus 85 degrees. It's 84.996. It's 85 degrees, effectively. Okay, so that tells me that we're not looking at 95 here. We're looking more so at 95 degrees here, which puts us in the third quadrant. And indeed, this is the number that I had selected moving into this example to begin with, where we actually have an eccentric anomaly value of 265 degrees. So what does this tell us? This tells us a number of things, that these two equations here can be used together to give us a value that is accurate. Like, we know where our orbiting body is in relation to our host body and the origin, so we can get accurate times of flight. The other thing this tells us is that we don't strictly need both of these equations in order for them to work, right? Because we looked at this value here and this value here, and we said something isn't quite right, because this only had us believing that our satellite appeared over here in quadrant 2, but we knew better than that our satellite was, at least in reference to the host body, in quadrant 3. So something was up. And really, that's the that's the main takeaway I want to give to you guys, is that you really only need one of these equations. You can have your... Scroll up. You can have your cosine equation that can give you a left or right of the origin. Or you could use your sine equation that can give you an above or below the origin, again, using the system that we've kind of arbitrarily agreed to for this series. And you can kind of piece together whether it makes sense or not of, okay, this body that is orbiting, yes, it belongs here, or no, it doesn't quite belong here. So now that I have given you that little speech, I think this is a good point to end the episode. So thank you all so much for stopping by, and I look forward to seeing you all in the next one.